Hello and welcome everyone. So what we have done so far, we have done gradient descent in the previous lecture. So I'll put a star mark over here because we'll come again to this gradient descent and we'll cover it in detail and different variants of this gradient descent algorithm once we cover the back propagation, and then when we come to the implementation of gradient descent and different versions of it, then we'll again look into the gradient descent in detail. So today what we're going to see is a representation power of these MLPs. Representational power of multi-layer perceptrons. We did about two types of multi-layer perceptrons. So actually it was only one, so by adding some other non-linearity. So initially we had thresholding logic, and then we said, okay, instead of let's say thresholding logic, we can have a sigmoid, a smooth function. And we can have other activation functions as well. So now we'll see what is the representation power, how much can they represent and what can they do. Okay, the first thing that we'll discuss first is why are they called deep structures. Okay, why this deep? So if you know, these neural networks can be geometrically or can be written in a visual sense by using directly acyclic graphs. You might have heard about directly acyclic graph. What is a graph? So graph is made up of nodes, okay, and it's made up of edges. So this is a graph. It can be directed under, there's a huge graph theory which I won't get into. So let's suppose this is a graph. So this thing here can also be considered as a neural network. But you can see that so there is a concept of source and sink. So here these are called nodes and we have edges, and here this is a directed graph. So direct acyclic graph basically means where you do not have a cycle. So if you have a cycle, so you come back and the source and sink, basically you start from here. If you can come back to that node, if it is a directed graph, then we call it a cyclic graph. The acyclic graph means where there is no cycle. So now we'll define this neural network in terms of this directed acyclic graphs. As I said, this neural networks can be represented by these directed acyclic graphs. So in this we'll have source and a sink. So what is the source? So source basically in terms of neural networks will be our node input nodes, and sink is the output. So in terms of graph theory, source is which does not have any incoming edge, and sink is which does not have any outgoing edge. So in terms of graph theory, so now you have the source and sink in these graphs. So now if we draw let's suppose any neural network, we'll draw something of this sort. So usually we draw like this. So this is input, and then we have some hidden layers. Today we'll see in detail, like we'll also introduce some notations also. So this is where you usually see them. So this is the flow is going towards from left to right. So now if we draw a graph, so in order to define the depth first, so we'll see what is depth. So in order to define that, consider this is the graph. So we have three nodes in the graph. Let's suppose these are the three nodes. So now I'll draw some edges. So this is the first edge, the second edge, and the third edge. Now you can see that this is a directed acyclic graph. So now if you see what is the depth of this, so depth basically means if this is the source node, and let's suppose this is our sink node. So what is the longest distance? Okay, so or the longest path. Okay, the number of nodes or edges that come on the longest path. Okay, here if you see there are two edges. So if I can define it like this, number of edges on the longest path. So here you can see from source to sink we have 1 and 2. So we can say that the depth of this directed acyclic graph is 2. Okay, similarly I can let's suppose form some other directed acyclic graph with couple of nodes like this. Okay, so here we have an edge, edge like this, and this. This again is a directed acyclic graph. If you see, now if you see, this is the source. Source doesn't have any incoming edge, and sink which doesn't have any outgoing edge. So this is my source, and S dash is my sink. So now what is the depth of this? So if you see, we have to see from source to sink what is the longest path, the number of edges on that path. So if you can see from here, so I think 1 and 2, 1, 2, and I think let's add one more so that this can be a bit different then. Okay, so I want its depth to be 3. Basically you can just construct this graph somehow so that number of edges on the longest path could be 3. Number of edges on the longest path from source to sink, So here in this case I wanted to make graph such a way so that it is equal to 3. So basically this is the meaning of depth. So in nutshell, what is the meaning of depth? So if you have a source node and you have a sink node, number of edges on the longest path. So now if you have to define the depth of a neural network, so in the similar fashion, as I said, source is the input node and sink are the output nodes. So now if you have to define the depth, so you will again use the same definition that was using direct acyclic graph. So you'll say that the longest number of edge number of edge on the longest path. So if I now make a neural network of this sort, so usually you'll see neural network like this. Consider this as input. Okay, let's suppose these are 4 inputs. Then we'll have some hidden layers. Okay, something of this sort. So now you have edges like this, something of this sort. Now you can see that if you take any, here we have, these are the sources because these are the input nodes, and here this is the output layer. So if you take any source node to any sink node, you can see that the number of edges is 1, 2, 3 and 4. So you can say this deep learning network, this deep neural network has depth of 4. So why am I giving these formal definitions? Because how is deep defined? So any network where depth is greater than 2 is called a deep network. So these are the formal definitions. So the first formal definition of depth. So the number of edges on the longest path from source to sink is called as depth. So in this case, if you see, then this is called this network has depth 4. And now what I'm saying is a deep network will be called a deep network, or a network is called deep if the depth is greater than 2. So if you see depth is 2, then we do not call it a deep network. So depth should be greater than 2, 3, 4, 5, 6 and so on. So we'll call that a deep network. Is it clear what is meaning of the depth and what is a deep network? So I think it's pretty basic. And second thing we'll see is what is a layer. Okay, so how do we define layer? So if you see this, let's suppose now you can see over here. So which nodes can we call that they belong to the same layer? So let's suppose this is our input. So you can have nodes like this, something of this sort, even if the network is not made like this. So formally how the layer is defined. So what you can do is, if this is the first edge and let's suppose this is second, and here this, I just make something random so that okay. So now I have made if you see this node, consider this node, the one I colored with the pink color. So now the longest path over here is 2. Okay, if you see the depth of this node actually is 2, so this will be considered layer 2. So the depth of node will give you its layer number. So now if you consider this node, so this node is connected only via one edge. So now no edges there. Other than this, there is no edge. So this is at layer 1, this node. So I'll just write layer 1. So again, if you consider this, again this is again layer 1 because the depth of this node is 1. So now if you consider this, so there are some paths over here, but the longest path is this. So if you consider from here to here, okay, so the depth of this will be 2. So this node will be considered in layer 2. So now if you are given any neural network, so if you are asked to demarcate these neurons, what is the layer number they should be given? So what you should do is you should consider the depth. So whatever the depth of the neuron, that neuron will go to that layer number. Okay, is that clear? So we discussed 3 terms. First we discussed what is depth, and then we discussed what is meaning of a deep network, and then we discussed how to demarcate these neurons, how to assign them layer numbers. So depth, basically what I said is the number of edges on the longest path from source to sink. Okay, from source to sink, what is the longest path, and count the number of edges on that. What is the deep network? If the network has greater than 2 layers. Okay, and basically when you have this, when the depth of the network is greater than 2. So how is a neuron assigned a layer? So whatever is the depth of the neuron, so it will be assigned to that layer. Is it clear? So these are the basic definitions which you should remember before the subsequent discussion. So if this is clear to you, now I'll introduce very important notations which we use throughout. So these notations are very important because we'll be using back propagation, and then we'll have to derive the equation of back propagation, or wherever we are using these neural networks, we'll use this notation. So I'll try my level best to be thorough with this notation, so that wherever I use it, I'll try to use the same notation, not deviating from the notation. So what is the notation now? Okay, let me form a network first. Let me draw a network. So this is our input. Okay, and you know how we represent data. So data is represented like this: xi and yi, and I goes from 1 to n. This is how data is represented. Now if I take just one point, so x1, let's suppose x1 will have x11, x12, x13, and so on, x1n. So this is one data point. So these are the features, the first feature, second feature, third, fourth, fifth, and so on till nth feature. So this is our data, and this is our corresponding label. Now in this case, let's suppose we have three inputs. We have x1, we have x2. So let's suppose we have x11, x12, or xi1, i2, and in, or let's suppose i3 in this case. So this is our input layer. So I'll use this notation throughout, and then we'll have in between, we'll have layers. Consider this again. We'll have 1, 2, and 3. Let's suppose we'll have again 1, 2, or rather I'll copy this to save time. Copy, we can paste a couple of layers in between. And I have been telling you these are called as hidden layers. Why are they called hidden layers? Because we do not use their output directly. Okay, their output of these layers gets used maybe in some intermediate steps, but we do not use them directly. Okay, let's consider this. Let's say this is our final output. Then maybe like this. Okay, now we know that each neuron has two portions. One is the aggregation function and one is the activation function, something of this sort. Okay, and at the end we apply some other activation function usually. Okay, now this is input and this is our output, and these are our hidden layers, which you already know. So now I have to introduce notation for these. Okay, so that notation should be same throughout. And now what you can see is I can add these weights and biases. Let's use this red color. So we can have arrow going from here to here, here to here. Okay, these are my weights and biases. Okay, these are the weights, and bias usually is written within the neuron. Okay, same with this. Okay, now we'll remark these. So you saw that input is represented by this. So input is represented like this, and now each of we have weights over here. Okay, so how are these weights represented? So we represent them by a matrix W1. I'll write it in the superscript. So W1 is the matrix of weights which is in between layer 0 and layer 1. Okay, so this is W1. So how is W1 represented? So W1, if you see, this is a matrix which contains these weights. So if I talk about this, so here we have this input, and then it goes till here. So how can I assign weight? So this is, let's suppose, 0th layer, and this is first layer. So I can say this is W. So this weight over here, this is W, and I can say it goes from 0, let's suppose from layer 0 and neuron 1. So this is layer 0 neuron 1, if you see this. Okay, and then I can say it goes from layer 0 to neuron 1. So this is basically, I can write W1 in between this, and then it goes from this to this. I can even start from 0 or 1. I'll have to decide here. So consider this as first neuron, this is also first neuron. I can say this goes from, like, let's suppose 1 1. Okay, 1 1 of this neuron, and again similarly, then I can say this W. So now this is the second neuron, so I write 2 1. So this is the reverse, this is reverse. So usually it's written in reverse, so it will help us in back propagation. So again, if you take this neuron, so this will be W 3 1, and constantly we will add 1 at the top. So if you see this, so how are weights written now? So I can write it like this: weights W1 1. Okay, and then I can write weights W1 2, W1 3, and I have to also add biases. So will have this W1, and similarly we'll have bias 1 also. So in this scenario we'll have also biases for the network. So I'll write W1 here and B1 over here. So this will be having a matrix and a vector. So we'll have W1 like this, and then we'll have bias B1 like this. Okay, in this case, if you see, bias will be B11, B11, B12 and B13. So similarly, if you see this, so we'll have W11, W12, W13, something of this sort. And now this is 3 input, so this will be a 3 cross 3 matrix over here, and this will be 3 cross 1. Okay, I can write this W. So this is rather 2 1. So I should be writing it 2 1, W21, W31. So because you know I am writing in the opposite way. So this is going from, let's suppose, 1 to 1, 1 to 2, but I am indexing it in the opposite direction. So now if I write it here, so this, if I write Wi, so this means this is the weight matrix. This is weight matrix between I minus 1 and ith layer. Okay, and you know that we demarcate it from 0th layer. So this is our input layer is known as 0th layer, and then we have first layer, second layer, and nth layer, or lth layer usually. So this is our 0th layer, and this output layer is our lth layer. So this is 0th layer, and this is lth layer. Is it clear so far? Notations clear? So we have Wi matrix, that is the weight matrix, and similarly Bi. So Bi, this is the bias vector that we have. So it is also in between this I and I minus 1. So I minus 1 and ith layer, it's also in between these. And now how do we demarcate? Then we have activations. So in between, let's suppose you have this, you define it like this. So here, so I'll just remove these so as to remove the clutter. Now if you see this, so from in order to go from here to here, we define the weight, and now we have to apply activation. So we also define A1 over here. Okay, this is when you apply these functions, and then let's suppose you aggregate this and you get A1. After application of A1, you will apply an activation, so we'll get H1. So okay, so I'll write this. So let's suppose you have this AI. So what is this AI? So if you see how do we get this AI? So AI basically we get by writing BI plus, you just write this W1, so you get Wi, and then X, whatever is the previous. So previous here, if you see this, so this is H1, so here it will be H0. So before this was H0 actually, so all these will be called H0. So this will be Hi minus 1. So AI is equal to Wi Hi minus 1 plus Bi. So this is our aggregation. So when we aggregate, after we apply activation, so we have to apply activation. Let's call this, let's sigma or activation. Okay, sigma of AI. So that is called as Hi is equal to sigma of AI. So after we apply activation. Is it clear? Can I assume that you are understanding it? Okay, as I said, I have to be very thorough with the notations because we'll be using these notations throughout. That's why I'm being very careful today. So now what we defined is, first we defined weight matrix, and then we defined bias. This bias is a vector, and then we defined this AI. So AI, if you see here, this will be A1. So this will be H1 now. So H1 is after you apply this activation. And now if you see this, so this will be A2. Okay, and then this will be H2. H2 is after you apply a activation function on this A2. So that's how I wrote over there. So this is our aggregation function. Aggregation function. Or this usually you can see in the books. Sometimes it's written as, this is our linear function. Okay, or sometimes it's written as affine transformation. Okay, so this is affine transformation. I'll tell you what affine transformation means. So if you have, let's suppose, just a side note, so if you have Wixi is equal to 0, so this is called as linear transformation. You know why linear? Because this is a linear combination of these weights are taken. So if you write Wixi is equal, let's say, minus b, why do you write plus b is equal to 0? So because now you shift the whole linear surface. So this is called as affine transformation. So this is called affine transformation. So here if you see, many other times you will see either linear transformation, and affine transformation is also linear transformation. Okay, so this is usually written as linear transformation, or like in good words of mathematics, we can write it affine transformation or aggregation function or linear function. This is called as activation function or non-linear function. Activation function or non-linear function or non-linear transformation, because its function is also a transformation. And one more thing that we have seen over here, so we saw if this weight is written as Wij, so this basically means, so the weight is, this is between a neuron. Let's suppose if this is ijk, so this k is layer number. So this is the layer number coming after. So whatever layer number is after, so before that we write. So if you have wk weight matrix, that means the kth layer is next. Okay, and then this ith is j. So this is to and this is from. So this is going actually from this jth to ith. So why am I saying we write it in reverse? Because it is our calculation. So that's why we have these weights. And then you have these biases also. So similar, we can do it for biases also. So bias of, let's suppose k, this again will be a layer number. Okay, so if I, because bias also goes from I to j, so if I write I, j, so this will be to and this will be from. Okay, any other notations? Okay, so all in all, I think I have covered almost all the notations. Okay, so we have weights, we have biases, and then we have activation. And that's why this is called as hidden output, hidden. So that's why we see hidden over here. So if you see, this is H naught. So basically 0th hidden layer. Okay, and then we have H1. This is the first output of the first hidden layer. And this is A1. A1 is when you aggregate all these functions. So hidden, you get hidden output after activation. So this is A1, H1. And I think, yes, I think these are the notations. Is everybody clear with the notations? So if I miss some notation, I'll come back to you maybe after that. But I hope that everything is over here. So we defined weight matrix, we defined bias vector, we defined hidden layers, we defined input output, we also defined how data will be defined. Yes, last. And if you see this over here, lth layer. So how will the lth layer be shown? So lth layer usually is written as HL like this. So because after this you will get lth layer output. So, or this can be written as prediction, or this can be written as prediction of this sort. This is how we can write the output from the last layer. Okay, and we can write it like HL. So this is lth layer. Okay, so HL is lth hidden layer output. So basically this is the final output that we have, final output. Okay, or we can write it like this, y hat, or we can also write it like f of x, and that is prediction, the prediction function that we have. I think I have covered almost everything. Yes, so you should be clear with these notations. Again, just going through again. So we have input layer, we have hidden layer. So why are they called hidden layers? They're called hidden layers because we do not use their input directly. So we somehow use this intermediate input and then process it again. Now in order to see the notation, you have these weight matrices and you have these biases. So in here, if you see this, so this here, because input is n, and also here the output also is n. So this will be an n cross n matrix in this case. Okay, so let's suppose if this was n, okay, and this was some k, so this will be n cross k matrix. Okay, so it depends what's the matrix. So all in all, what you are doing here is, this is just matrix manipulation. So in training of neural networks, or when you do anything with neural network, you usually are doing matrix manipulation. So which I said is, we have this weight matrix. So what's the size of weight matrix? Depends on because this w1 is defined between 0th and the first layer. So if you have wk, it is defined by k minus 1 to the kth layer. So when you have wi, that is the weight matrix between I minus 1 to ith layer. So now what is the size of that? It depends on how many neurons are here and how many neurons are here. So if k number of neurons are here, and if let's suppose p number of neurons are here, so the weight matrix will be k cross p. So this weight matrix will have. So if you see this bias, so this bias vector, because it depends on how many inputs are coming. So each neuron over here. So if you see 1, 2, 3, all of these will have their own biases. So the number of neurons will tell you the bias. So it usually is. So you have wi matrix, which is k cross p. Okay, because you write w cross x, let's suppose. So all the time, if you have first neuron, so first you should be very careful. So if you have wi, so wi in this case, let's suppose if you have w1, so what should be, because you do wx plus b. So what you try to do is, if you have this w1, so the dimension should match. If the input is n dimensional, let's suppose input is n dimensional, input is usually n cross 1. Okay, and this should be n cross, let's suppose. So if you have the other k cross n, something of this sort. Okay, so you usually will write it as n cross k, because you take a transpose of this after that. So you'll usually see it written like this, w transpose x plus b. So whatever matrix you have, you'll take a transpose of that. Okay, it depends how you represent data in your neural networks, and based on that you have to apply transpose. Sometimes if you write it in such a way so that the transpose is not required, but in this case, if you define it like this, so as I have defined over here, so I have defined it like this, k cross p. So you'll have to take transpose. It depends how you define it. Okay, I hope this is clear. So then you have this vector bias vector. So because you are taking this transpose now, so you have W is n cross k. Let's suppose now you take a transpose of this and then you multiply it with the x. So x is the data matrix in which you again basically are seeing that you have n features, and then you have, let's suppose, some x data point. You have some, let's suppose, z number of data points. So this again can be a matrix, or you can just take one point of that. So now you have to also add bias to that. Okay, if I just talk about one data point, say we talk about just one data point, n cross one data point. Now you can see that this is k cross 1, and this over here, the bias over here should be k cross 1. So this should be a vector which contains k number of elements in this. So this should be the bias. So you should take care of dimensions. So big note here, take care of dimensions. Okay, define based on this. So should you apply transpose, should you not apply transpose? It depends how you define this weight matrix. So we have weight matrix and you have bias matrix, and then you also have data. So you have the data matrix as a whole. Then you perform the multiplication in one go. Okay, when you have to apply forward pass. I hope that you're clear with this now. So in order to now define, let's suppose if somebody asks me, can you define this neural network in terms of mathematics? So what I can do is, so basically how it is happening is, so you have this AI of x. So before you have to aggregate this. How do you aggregate? You take bi plus you take this wi hi minus 1, which I earlier showed. So this is, so whatever x you are getting. So let's suppose pre-activation layer, which we'll call pre-activation, and then you will apply activation on this. Okay, you will apply activation. So activation will be hi of x is equal to g of ai of x. Okay, which I earlier showed you. This is activation layer, and this can be you can have a different function over here. Okay, you will have weight matrix, something of this. Let's suppose w1 can be defined. So in this case, we have 3 cross 3 matrix. You'll be given numbers like this: 0.5, 0.2, 0.3, 0.1, 0.8, 0.1, 0.3, 0.1, 2, 0.6, or something of this sort. Okay, this will be weight 1 matrix, and then you will be given bias 1 vector. Okay, so you will have something of this sort. So you can write it in transpose also the way you define it: 0.1 minus 0.1 comma 0.2, and then you will have to apply. You will have, similarly you will be given w2 bias 2, w3 bias 3, and you will have to apply this sort of notation on here. Okay, I hope this is clear. I hope this notation is clear, and we will use mostly, I will not try to deviate from this notation when I am deriving the formulations, or if I am using it, let's suppose in PyTorch, or if we are making our own library. I'll try to abide through these notations. Maybe I can sometimes deviate, but I made sure that, because sometimes I can do this transpose and sometimes I may not do transpose. It depends how I define data matrix. Okay, we'll see it there, but I hope that you got the notion how did I define these things one by one. Can I assume that everybody is clear on this point? Now that we laid the foundations, we at least said that, okay, now we are clear with notations, we know what depth is, what a layer is, okay, and we know all these terminologies. Now we'll see representational power of these multi-layer perceptrons, basically what they can represent. The first thing is these multi-layer perceptrons, multi-layer perceptrons can model any Boolean function, that we have already seen. So I'm again showing it because today we spoke about depth. I want to show you that how is depth related. So how can we see the width and depth, how are they related? So now you can see that we can, let's suppose, have a gate, so of this sort. Let's suppose input is x and y. So say these are 2 inputs. So I can give 1 and 1 to weights over here. So if I say threshold is 2, if I apply thresholding logic even, so I can say that this is our AND gate, x and y. So once these inputs are on, the threshold will be 2, then only this will fire. So we can similarly model XOR gate, not XOR gate, so this is OR gate, and this is we can also have NOT gate and other gates. So you know that single layer of single perceptron cannot model XOR, and we have also seen what's the problem with that. So why can't it model? So now I'll give you one. So basically, what we actually today I want to do is I want to show you what is the how can I compare the depth and the width. So now you know that if I have any type of Boolean function, okay, how many neurons, like if I only have a single layer, so what do you think, how many neurons do I require? How many neurons do I need? How many neurons do I need in the first hidden layer? If I only want to have this first hidden layer, you have seen that that because we want to model each of the combination. If I have an input function, so if I have an input function, and you know the possible combinations are 2 to the power n, and we saw that we can model this by using 2 to the power n. In worst case scenario, we can do this. Okay, so let's see, can we do something better than this? Can we somehow decrease the number of these neurons which we can use? Okay, so this is the case that we want to do. Okay, I'll take some, let's suppose, some examples. The example that I'll take, let's suppose, is of this nature. So I'll have a Boolean function, say of 16 inputs. How many of you know Karnaugh maps? Do you know K-maps? So I can directly write this table into K-maps. So I'll write truth table in K-maps. So what are these Karnaugh maps? So if you see this, so let's suppose we know that if we have 4 inputs, so how we can write 4 inputs is, let's suppose x, y, let's suppose p, q, r is something of this sort. So we can say 0, 0, 0, 1, 1, 0, 1, 1. Again 0, 0, 0, 1, 1, 0, 1, 1. So this is the K-map of that function. Let's suppose if we have 1s over here, so 1, 1, 1, 1, so 1, something of this sort, 1, 1, and rest we have zeros, let's say. Okay, now in order to, we can directly take this. So wherever we have 1, let's suppose we have 1 this, we can write p, q, r, s, bar, bar, bar. So because we have this 1 over here, so this is p, q, r, s plus. Okay, because wherever there are 1s, I have to make these neurons active. Okay, rest I can leave them. And you know how to create digital circuits for that. You just take these 1s place and then you make a gate out of that. Similarly, you can take this. So this is p bar, q, r, s, bar, bar. So bar basically means wherever you see 0, and without bar is basically 1. So this is called as DNF, disjunct to normal form. What you do is you basically take ands wherever you see 1, and then you or these together. Okay, so if you want to see a detailed K-map, you can just refer to any of the material where you can get the information about K-maps. So this is usually how it is defined. So if you have a truth table, so you can define it like this. So now you see this one, wherever we have ones, you can club them together. Okay, you can club these ones together. Okay, you can club these ones together. You can club these ones together. So you can create what's called as minimal DNF. Okay, I can write this maximal DNF. So basically maximal DNF means, so I can write all of these things together. So I wrote for this one, then I wrote for this one. I can write for this one plus p, q, r, s, bar, 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 plus I can write for this one now. This is p, q, r, and s, bar, bar, because rs here, if you see, this is 0, 0. And then I can write for other 3 as well. Okay, other 3 in the similar fashion. So this is at disjunct to normal form, but this is not the minimal form. Okay, this is not the minimal. So what you can do is, you can basically apply Boolean algebra on this to get a minimized form. So why do we want minimized form? Because whenever you want to make a circuit, you usually, if you have a bigger expression, you want to minimize the expression, and then you make the circuit for that minimal expression, because less gates will be used. Okay, is it clear? That's where K-maps came into the picture. You don't have to perform Boolean algebra by just seeing symbols. So you can, as I said, you can club over here. So what is the meaning of this? How can I club all 4 of these? So this basically says, if RS is off. So if both R and S are off, no matter what the value of PQ is, it's always on. So that's why I can club all these 4. So from this DNF by using K-maps, so I can get K-maps, I can get minimal DNF. Well, these are called, these are also equivalent, because whatever DNF you have with this, with all these ones. So what you can do is, by using K-maps, you can shrink it down and the circuit will perform equivalently. So whatever circuit you will get with this DNF, and then if you apply K-maps on that, if you club these terms or apply Boolean algebra on that, so you will get minimal disjunct to normal form. Okay, is it clear? Can I assume that you understood this? Okay, now once you have this, so what I can say is, so you can create less neurons, because now if you have this DNF, so once you have this DNF, so the number of the terms in DNF, so these many number of neurons will be used. Okay, I hope this is clear. Okay, let me give you an example. So let's suppose if we have a K-map of this sort. If we have a K-map of this sort, say this is 1. So the K-map I made. So this and this. So these are 1s and rest is zeros. Okay, so what I can do with this is, so now if you write a reduced form of this, if you write the minimal expression, so how many terms will be there? So let's suppose this is w, x, y, and z. Okay, so if I write reduced form of this, so this is 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. So I can club all 4 of these. So the output of this will be equal to y bar z bar. So because this is where all are on, and then I can club these two also. Then I'll get 3 terms. I'll get plus w bar x y bar. So by using this, so you have to include this, and you have to include one of these. Okay, and plus I can include these. Okay, plus this is x bar y z bar. Okay, now I got these 3 terms. So if I got three terms, what I do is I can just have 3 neurons. 1, 2, and 3. So one will handle this, one will handle this, and one will handle this. Then what can I do is I can just OR them together. Okay, to have an output, I can just OR them together. Okay, so basically this will handle this 1, 2, and third term, and then this is the OR gate. And these are the number of neurons I use. So I use this is input. So my input will be w, x, y, and z. So I can give the input based on this, so that y, z will go to this, let's suppose something of this sort, and w, x, y will go to this, w, x, y, something of this, and I'll give the input in such a way that each of this neuron handles each one term in here. So what I can say is from this, I just can use the hidden layer, can just use 3 neurons. So otherwise, what is the usual case? The usual case that we knew is that if you have n inputs, we were using 2 to the power n neurons. So now I am reducing the number of neurons I can use. Okay, is the goal clear? The goal here is I want to see what is the minimal number of neurons that I can use. Is it clear? Is the goal clear? Okay, so that you don't lose the track, what I'm showing you is that we want to see that how many neurons, if we have just one hidden layer, so how many least neurons can be used. So let's suppose we are now seeing that 2 to the power n neurons we can have any function. But in this case, what I'm saying is if you are given a function, so this is a Boolean function, and you can apply Boolean algebra on it. So if you have n inputs, the total possible combination 2 to the power n. But you know that if you have this Boolean function with 2 to the power n, so you can use k-maps to get to a minimal DNF, minimal digital to normal form. So where you will get some terms will be eliminated, so you will get less terms than the original one. So from those less terms, you know that one neuron can handle one term in this case. So and then you can reduce the number of neurons that you can use. Okay. So what is the largest irreducible DNF? So what is the largest irreducible DNF? So what do I mean by this? So I should be getting a k-map which I cannot reduce. I have to anyway write all the terms. So in that case, what is that? So if you see, if I have a k-map of this sort, so I'll write something of this. So these are 16 things. So I'm just writing with 16. So you can later on expand it to any variable. So I'm writing here for n is equal to 4. Okay. So n is equal to 4. So we have 2 to the power 4. That's 16 combinations. So what is the largest irreducible DNF? So if we have a DNF which we cannot reduce, so that will be irreducible. We cannot reduce that by using k-map. So that means we should not be able to club like this. So we can club 2s, 4s, 8s. So we should have a k-map in which we cannot club these 2s. So let's suppose I can start from here. So what I can do is I can have a checkered board. So in that checkered board, I'll have no way of reducing. I'll have this and then this. Okay, something of this sort, and then this, and this, and this. Okay, let's suppose this is w, x, y, and z. So now by using k-map or by using Boolean algebra, I have no way of reducing this. So I have no way to reduce. So which terms do I have to include? I'll have to include the terms, all these half terms. Okay, can you recognize this? Whose k-map is this? Can you define this gate if you can see it? So this k-map is for XOR. So you take your time later on and to think why is it the k-map for XOR, because so this is called, XOR is called as modulo 2 gate. Modulo 2. Okay, when you perform the modulus by 2, if it comes to be 0, then XOR is off. If it comes up to be 1, then XOR is gate is on. So you can see this is for XOR. So now you saw that. So you have 1, 2, 3, 4, 5, 6, 7, 8. So now this is the worst case possible because you cannot reduce the k-map in here. So what is the number of hidden neurons that you should use them? So this is 2 to the power n minus 1. Okay, you can use 2 to the power n minus 1, but you again have to use one more neuron to perform the OR. 2 to the power n minus 1 minus n. So this is the number of neurons that you have to use if you have one hidden layer. So if you have one hidden layer, so in XOR, because this is the largest irreducible DNF, okay, because I cannot reduce it. How can I reduce it? If I can club terms together. Here in this case, I cannot club any term together. So now with one hidden layer, so I have 2 to the power n minus 1, because I only have neurons for these, where you have this one. but the gate is off, I don't need to consider that. Now this is 2 to the power n minus 1. Initially it was 2 to the power n. Now we had divided by 2. So 2 to the power n divided by 2 is this, because where half inputs are on and half inputs are off, if you see this. Okay, rather not inputs, half outputs are off. Okay, so the output of the function, for half of the combination it's off and for half the combination it's on. So that's why we are 2 to the power n divided by 2. That's 2 to the power n minus 1. So then we have one more layer. So one more neuron will be used for OR. So you have, let's suppose x1, x2 till say xn. And then what we will use in the hidden layer in between, you will have 2 n minus 1 neurons and then plus 1 neuron so as to perform the OR of this. Okay, so these many neurons will be used if we just have one hidden layer. So this is the number of neurons. Number of neurons that will be used. So what I did is, again coming back, so I said, can we reduce this somehow? So we said if we are given any Boolean expression, so how can we reduce? We can make k-maps. So we can see that if we are able to club some terms together, then we can reduce this DNF form, we can reduce this disjunctive normal form, and we can have a minimal expression, and which can be then we can use neurons to implement that, and one number of terms in that minimal DNF is the number of neurons we'll have. Then we said, is there a largest irreducible DNF, so which we cannot reduce? So we came to this conclusion because we were clubbing the terms in k-map if there was a bit difference was only 1. So now on purpose we are making this checkered pattern. So why are we making this checkered pattern? Because we do not want this DNF to be reduced by using k-maps, okay, or by using any Boolean algebra. So this is the largest irreducible DNF. So what I'm saying is now, so now if we only have one hidden layer, so how many number of neurons will be used? Because we'll only have neurons for the terms where we have this 1 1 1. Okay, for the other patterns, for the other bit strings, for the other combinations where the output is 0, we will not have neurons for them. So the number of possible neurons is basically 2 to the power n divided by 2, that is 2 to the power n minus 1, and plus one more neuron, because we are performing OR operation of that. So this is the number of neurons we can use. So if you are asked that, so what can you in terms of XOR? So we have to use, if within one layer we have to use this. So this is with just one layer. Can we somehow do something? We can make this network deeper. So if we can make this network deep, so can we somehow reduce the neurons? So that is the question now that we are going to answer. So if now we saw that with one hidden layer, so XOR function, because we cannot reduce it, we have to use 2 to the power n minus 1 plus 1 neurons. That's exponential number of neurons. So if you have n inputs and you have only one hidden layer, okay, then you have to use 2 to the power n minus 1 plus 1 neurons, and this is exponential number of neurons. If you see over here, exponential number of neurons. So what is the problem with using exponential number of neurons? The problem is that you have to implement this in the hardware. Okay, that you have to use exponential computation. Okay, this is the problem with this. So now we are going to deep networks. So why are we resorting to deep networks? So the answer to the question is that we first want to look, so can we somehow use these depth and we can trade off with width? Can we somehow decrease the width and then we can trade off with the depth? And can we go to linear? So if you see width, so width was exponential, and it is pretty hard to train. So if you have to train it, because it will use exponential number of neurons to compute, and you will see how much resource intensity it would be. So I want to see if I can make the network deep. Is there a possibility that I can make this network deep? Okay, so that I can go to polynomial number of neurons. So you have exponential number of neurons, then you have width, basically one hidden neuron. So we have one hidden layer or some hidden layer. So then you have to use a lot of neurons. So can I have a trade-off? Can I make this network deep? So as I can use polynomial number of neurons? Okay, we'll see in terms of XOR, because in our case, XOR was a function in which we couldn't reduce this DNF. We couldn't reduce it to the minimal DNF, minimal disjunctive normal form. Okay, we'll see this. Okay, now what we can do is, if you see this, I'll again make this checkered board. So checkered in that case was, so let's suppose in checkered we had, I can copy this checkered one. So in this was a checkered one. So this case was the checkered one. So I can write these 8 terms. Okay, let's write it like this. We can have XOR of, so call this is XOR of U XOR. So this is U V W X Y and Z, something of this sort, because we have these many number of terms. So consider this. So if you have this U V W X Y Z, so U XOR V XOR W XOR X, Y, and Z. Consider these are the terms. Now you know that if we have to implement this, so we have to use at least 2 to the power n minus 1 divided by 2 number of neurons. So what we can do is, now you know that XOR is an associative operation. Okay, so what I can do is I can use this U and V. So I can say U, V, W, X, Y, and Z. So I know that this is an XOR operation. So I can club these things together. So I can say U and V, I can perform this with 2 neurons and then perform one more with 1 neuron. Let's suppose I'll use for this term, so U XOR V, I can perform with 3 neurons. Okay, so this can be performed by 3 neurons. So this U XOR V. And now I know I should not start from initial, I can go from here now. So this will be now one more neuron and one more neuron like this. Okay, now if you see, this neuron is at depth 2. So this is at depth 2. So this will be considered in the second layer. Why? Because it goes from, it has 2 edges. So one from here W and then between this. And this is the layer 1 over here. So this over here is layer 1. So this is layer 1. These 2 neurons. And this is layer 2. Okay. So this again is layer 1. So now this can be considered layer 3. Okay, this is at layer 3. Sorry. So you have to construct the maximum number of neurons. So this is layer 1. So these things are, this is at layer 2. This is at layer 3 now. So layer 3. Okay, and this one again is at layer 1. So now you performed U XOR V. So here you performed U XOR V XOR W. So again with this, what you can do is this over here. You can again perform XOR, and you keep on doing this XOR. So initially, what was the what would have you done? So you would have done, let's suppose 2 to the power n minus 1. That is 2 to the power 3. Let's suppose 2 to the power 3 plus 1. So let's suppose 9 perceptrons would have been used. So this network, I think, let me check the calculation. Wait. Now if you see, so we had 1, 2, 3, 4, 5, and 6. So we would have used 2 to the power n minus 1 plus 1. So that is 2 to the power 5 plus 1. So this is equal to 33 neurons we would have initially used if we directly use the DNF form, and we could have reduced this. So what I said is, but by using this depth, because now we use this depth, so we can keep on increasing the depth. So how many neurons will we use? Because we are using 3 neurons for each of these pairs. So this is 3 neurons and 3 neurons, because we have 5 pairs now. So this is 3 multiplied by 5. So this is equal to 15 neurons. So initially, now how many were we using? We were using 2 n minus 1 plus 1. So these number of neurons with one hidden layer. One hidden layer. Now if you increase that number of hidden layers, so what I can do is I will use 3 into n minus 1. Okay, 3 because 3 is used. We need now the number of layers. So how many number of layers are there? So I think the number of layers are log 2n. So the number of layers. So this is after we reduce. So this is one hidden layer. So this is with more hidden layers, with more hidden layers. Okay, so how many layers? So because each time it is reducing, this n is reducing by 2, and then we have to add one more neuron to perform this. So here if you see, we are reducing this layer 2 to 2, but we have to add 1 neurons here. So 2 and then 1 layer. So we have to after each reduction we are increasing 2 layers. That's why log n layers, but 2 times this log n. So this is the number of layers. So this is the number of layers. So I again summarize this thing. So now you can see that if you have only one hidden layer, so how many number of neurons you're using? Exponential. So now we are just doing this treatment on XOR. So in terms of XOR, because XOR was the this was the irreducible DNF form, okay, and largest irreducible DNF form. So 2 n minus 1 plus 1. So we had to use these many neurons if we have only one hidden layer. So when we increase the number of layers in terms of this XOR, so what we use it with more hidden layers. So the number of neurons. So this is number of neurons over here. So these are number of neurons. Okay, and now how many layers? So the number of layers, if you see, is 2 log n, because each time we are reducing the number of levels by we're halving, basically each time we are decreasing it by dividing by 2. So if you see, initially we had, let's suppose 6, we went to, let's suppose 3 over here, and then we have to add one more thing basically, but we have to keep on adding one. So that's why we're with this 2 log n. So why 2 log n? Because we are pairing the terms, okay, and 2 layers per XOR. So I can write the reason for this is we are pairing terms. By pair I mean we are clubbing 2 terms together, and the second thing is, and then we have to use 2 layers per XOR, 2 layers per XOR. So when we are pairing, so you are keeping a layer, and then for each XOR you have to use 2 layers. That's why the reason is 2 log 2, and these are the number of layers. Is it clear? So now if you see this, so in order to implement XOR, if we just use one hidden layer, if we use one hidden layer, so how many number of neurons are required? 2 to the power n minus 1 plus 1. Okay, exponential number of neurons. Okay, so now if we use multiple, if we are given liberty to use multiple hidden layers, so the number of hidden layers is 2 log 2 n, and how many neurons can we use? So we can use the number of neurons is 3 times n minus 1. Okay, and with this XOR is with n input. If we have n input XOR. So is it clear? So you started from exponential, so this is exponential number of neurons, and you now are at polynomial number of neurons. Can you see it? So now you have a solid reason to make the network deep. Okay, why? If asked, why are you making network deep? So there is a high possibility that if we use network deep, it will do the approximation of the function much better than if we just use a linear layer. And we can just give an example of XOR function. If you have an XOR function, because this function is the irreducible disjunct to normal form, so if you can reduce this function, there is no way you can reduce it by Boolean algebra. So if you just use one hidden layer, so what you can do is you have to use exponential number of neurons. But if you are given liberty to use multiple layers, so if you are given liberty to use layered structure in the neurons, then you can decrease the neurons from exponential to polynomial, and you can have the same, you can approximate the same function. I think we have a question. Yes, please.
Yes.
The questions that we received, the first question was, can we somehow reduce it more? Okay, can we, if we have number of neurons, because here in this case of XOR, so you saw that the number of neurons, if we just use one hidden layer, was 2 to the power n minus 1 plus 1. And then when we used a couple of like tricks, let's suppose we clubbed 2 terms, we basically used a pair of terms, and then we constructed a deep network. So we reduced it from 2 to the power n minus 1 plus 1 to 3 n minus 1. So the question is, can we reduce it further? Maybe or maybe not. Why maybe or maybe not? If I say we cannot reduce it further, then I had to prove the thing that I said. That give me the proof that this is the minimal number of units, or this is the minimal number of computational units that I can use. I have to give a proof of this. So rather than this, maybe some other people can come up with a clever technique. By the help of that, we can reduce it further maybe. Okay, there is a big if in this question. So can we reduce it further to approximate the function? But what I said is, I said that Shannon's theorem, it has proved that if n is greater than 2, so if n is greater than 2, what Shannon has proved is that it is not always possible that you can use polynomial number of gates. For some of the Boolean functions with n variables, you at least require 2 to the power n divided by n number of gates. So this is what Shannon proved. So this is Shannon's theorem. The question is it always possible to come up with the sort of construction of a network, or to come up with construction of a circuit by the help of which we can have, let's say, polynomial gates. So what Claude Shannon said is, he said that if you have input that n is greater than 2, there is a Boolean function in these n variables, okay, that requires 2 to the power n divided by n Boolean gates. Okay, so regardless of its depth, so how much depth you are given liberty to increase depth as much as possible, still you can come with a function that requires this. So as I said, one more thing that I said in here is that if Boolean functions or n inputs could be computed, so if you are saying that we have a Boolean function which has n inputs, if we could have a circuit, if we have a circuit of size n, that is polynomial size, okay, and if we have n input, we have n input Boolean functions, and if we can have a circuit of n size for that. So basically what you are trying to, you are proving n is equal to np. So if you somehow prove this, so you can have a circuit for all this n input Boolean functions where you can compute the whole thing is in polynomial time, that is in n. So you are indirectly proving n is equal to np, and you will get a $1 million prize. So that's the first question asked. Very good question. Can you reduce it? Question second was if we can reduce this, because we have this fully connected layer. So we have this fully connected. By fully connected, we mean that the neurons go from one layer to other, and all the neurons are connected to all other neurons in each of the layers. So layer 1 and layer 2, you will see that all of the neurons are connected to each other. So that's fully connected. So if we leave some connections, okay, so what are we achieving by leaving some connections? So what I said is, if you are leaving some connections, maybe you will gain some of some compute, you will lessen it by something, but you will not fully reduce the thing. Why? Because you still have the same size. So what is the meaning of size? So I can define size, number of computational units, number of computational units. So if you are just removing these connections, some connections, maybe you can reduce some computation, you can decrease some computation, but it will not reduce the computation units. Okay, it will not have much impact. So there I said that. So if you see a human, so human has 86 billion neurons. Okay, 86 billion neurons. So these are the computation units. So these are the computational units of a human. Well, how are they connected? So okay, so they are connected by 100 trillion connections. Okay, so these are like our weights and biases. Weights and biases. So basically those connections, the synaptic connections we have between these synapses and within the neurons. Okay, so information, what I said is, if you have to see if a person is intelligent, so what usually is seen that, let's suppose this is our neuron, which we have seen in depth, and then you have these axons. So you have an axon, and then you have this dendrites, then synaptic terminals. So information basically comes to this soma, and then it gets transmitted via here. So I said that there is a covering on top of this axon, so that's called as myelin sheath. Okay, and that is made up of fat. So what we have seen in humans, that Einstein's brain was taken and it was compared with the average human brain. So it was seen that the neurons that are in the brain of Einstein, they had this myelin sheath was quite thick, so there was more fat. So more fat was present. So more fat was present in there. So the possible reason is basically when the transmission of information is happening. So because there is this insulation sort of thing, so the information loss is very less. Okay, so that is why probably people are intelligent, because of these connections. And now you have these 100 trillion connections also. Okay, so this means how much you are storing it, the information that you are storing. So what I said is, if you miss out these connections, maybe you are missing some information. Okay, but you are still not doing a very greater good by just removing the connection. If you are removing one computation unit, and maybe there you can reduce a lot of computation, because you are reducing these computation units. So you are reducing these things. So what happens basically is, you are giving you a network that you don't have this neuron now. You don't have this neuron. You don't have, in the forward pass, if you see, if there is no neuron, less computation. If there is less computation, less resource will be used. Okay, but now if you are reducing these things, you are giving it less degrees of freedom. Okay, less degrees of freedom. So what do I mean by this? Then I discussed about scaling laws. So what are scaling laws? Scaling laws are saying that if you have more data, these models learn better. Why? The question is why? Because we assume that data contains information. Okay, the more data you give, we are thinking that more information we are giving. Okay, so as I previously also discussed, that if you give just few points, so it is saying something about data distribution. If you now give more diverse data within the same distribution, so you are now nearly approaching distribution. So what is the actual real data distribution? You are approaching that by giving more data. So when you give more data, it is expected that model will learn better. Okay, second thing is, if you increase the number of parameters, that is basically you are giving it more degrees of freedom. So when you give it more degrees of freedom, so it can learn, it has now ability to capture more things from the data. Okay, data has the information and it has to be captured by the model. So how can a model capture the data? How can a model capture information from the data? So that is if you can give it more degrees of freedom. So when you increase parameters, or the model size, which we call as parameter. Okay, usually I don't agree with model size, because what I said is size is number of computation units, but there is a relation though. But when you say size of these models, they consider with these weights and biases. Okay, with weights and biases, they don't consider the number of neurons. They consider these weights and biases, because this gives more precise number of parameters that you have. These weights and these biases are parameters. So these neurons are now counted in the size. But usually when we talk about size of a circuit, so you say how many computation units are there, how many computational units are there, that's the size. So in case of these large language models or deep learning models, so the size is given by weights and biases, basically by these connections, number of connections we have, by this 100 trillion that we have in human brain. So if you increase this, you are increasing more, you are giving more degrees of freedom. So when you give more degrees of freedom, so there is a possibility to learn more. And then if you give more resources, so what will happen basically? So this will become easily trainable. So it will train faster. So when it trains faster, so it can compute gradients. It can, so precision will be more. So then the training will be much more stable, and the training will happen much more fast. That's what scaling loss is, and it is expected that this should happen till a certain point. Now after a certain point, if you increase data, let's suppose you have data which already is giving you the complete distribution. Okay, then there is no point in increasing the data. Okay, if you have model which has the ability to sort of understand or to sort of learn all the things that are there in the data, then you don't need a lot of resources. So here, so these companies are playing they are playing with these three scaling laws. Why? Because they say that we have a lot of data with us, nobody can beat us here. So we can increase the model parameter because we are the people who have only resources. Okay, they are leaving these small companies out of this. This was the second question that I asked. The third question, can somebody recall the third question? What was the third question? The third question was, if let's suppose tomorrow some other mod, can we reduce the circuit size more? So let's say if you have right now we are going to the polynomial circuit size. So tomorrow if something happens, okay, can we reduce this? Can we have smaller networks which can do this better? Maybe. Why? What I'm saying is that these and the computational model that we have right now, back propagation, gradient descent, everything, this is suitable for the hardware that we are currently having. And based on this, the network is performed. Maybe we can come up with a better computational model of a neuron. So if some other day we came up with better computational model, we came up with better learning algorithms, maybe we can learn from less data, because that's how humans learn. Humans learn from less data. And within humans, it also varies. Some people learn very fast. Okay, some people just see, let's suppose, some examples and they learn. Okay, it also varies among humans. So humans learn on less data, and as I said, it also varies among humans. And tomorrow somebody can come up with a better computational model of a neuron, or better computational model of learning and thinking. So whatever we call learning right now. And maybe you can reduce the network size more. So there I came to the question of efficiency. So what do we consider efficient? So as I said, humans are considered efficient. Why? Because the resources they are using are abundantly available. So if you see, where let's say breathing oxygen is available in abundance. So we are using water is available in abundance. And then evolution has somehow figured out a way for the humans so that whatever resources are available in abundance, or they can create these sources, and then they can run their machinery, or they can run their metabolism, and they can run their life processes on that resources which are in abundance, and they use least energy from this. So what I said is, right now in these machines we are using electricity as major resource, or we are using, let's suppose, a lot of hardware is also required. So, and to make that hardware and to produce electricity, we need a lot of energy. We need a lot more energy than is required for the humans. So maybe the second revolution which will be there, if we have these machines, they can do everything, but we have to make them cost efficient. So how can we make them cost efficient? We can make better source of energy for them. As I said, let's suppose right now the available energy that we have is lithium ion batteries. Okay, maybe we can come up with better materials which will have better energy density, and they can produce much more energy. If we are going to that, so we will reduce a lot of cost of these training models and stuff like that. But I suppose people won't, because of these scale law, because people want to be relevant, they don't want to be like these big companies. Rather, they don't want to lose their game, they don't want to lose that top spot. They usually won't fund the research which will reduce the energy, because they are like requiring more energy, more resources, more data is keeping them in the game. If this is reduced, the game over for them.